Let's talk about transfer functions. This is an extremely useful concept in controls. It looks very mysterious when you first look at it. Most people find it very complicated, but hopefully I can convince you that it's not as complicated as it first sounds. Okay, so there are a bunch of things to unpack. Let's see how we can go about it. First, let me start with a very simple robot. It's a single link robot, 1 degree of freedom. Very similar to what we did with 2R manipulator, but now with only one link. So let's say there's this black link with inertia I, mass m, and now we have a new thing which is the friction constant B, or really it's damping constant B at the joint. It's capturing how much resistance to movement is there at the joint. Then what we are already familiar with is the angle that the link is making with some reference horizontal, and in one link case the relative angle is the same as the absolute angle. We have seen that before, so let's call it Q like we have been calling it. And now let's imagine that there is a motor at the joint applying a torque tau. So this is the setting. It's a familiar setting, and we are assuming there is gravity. Everything is as usual, nothing fancy here. And we are going to make 3 assumptions, or really have 3 things in mind before we talk about what is a transfer function. Okay, so first thing, when we are talking about transfer functions, we are using only linear approximations. So transfer function is a tool that is extremely convenient when you're talking about linear approximations. But if things are not linear, it doesn't work very well. Second, in transfer functions, you always assume 0 initial conditions. That is for the convenience of derivation, and you'll see that in a minute. And the final thing is, now you switch your thinking a little bit to input-output thinking. In robotics, of course, we do talk about if you apply a torque at the joint, what is happening at the robot level. But in many other fields, like in mathematics or physics, you try to write a relationship between these variables as a differential equation without worrying about what is the input, what is the output. It's just a relationship between all the variables involved. But once you start talking about transfer function, you are now switching your thinking to what is the input to the system. In this case, the natural choice would be I'm applying a torque to the joint, so the torque is the input. And what is the output is what the robot does, and in this case we can say it's Q. The joint angle is the output. Okay, so with these 3 in place, now let's jump to how a typical transfer function analysis looks like without going into too much depth. I'm just giving you a flavor of what it is and how it's useful and how it's used. Okay, so for a simple robot like this, we can write a differential equation relating how any torque applied at the joint affects the joint angle Q. And this should also be familiar to most of you, particularly mechanical guys, but even other guys, in 12th standard physics you would have seen this, perhaps in first year mechanics courses you would have seen this, where you have a second order derivative of Q, so angular acceleration, so inertia times angular acceleration, this is the inertial term, plus B times Q dot, this is capturing the damping effect, how much resistance there is to angular velocity, plus the third term is capturing the effect due to gravity, and this is of course a linear approximation. Otherwise in general you would have gotten a sine theta term here, but assuming things are linear, you have mglq. This whole thing is equal to tau. Now bear in mind that Q is a function of time and so is tau. So which means both of these are changing with time. That's why it makes sense to talk about the derivative. What is derivative? Rate of change of the variable with respect to time. Double derivative is, second order derivative. So you take derivative of velocity, or in other words, rate of change of angular velocity with respect to time is the double derivative, which is Q double. Okay, so far so good. This is how a mathematical representation of the motion of the robot looks like with torque and Q. This is very convenient to do some analysis. You can certainly simulate, if you apply a torque, what happens to the Q by solving this differential equation, and there are tools in Python, MATLAB, and any number of other tools. And in math courses or physics courses, you will typically study at this level. But in controls, you have a slightly different viewpoint where you are trying to figure out what is the right way to choose your input torque for you to get a desired angle or Q. So you are trying to work backward where you have something in mind of what the robot should do, and you want to figure out how to control it to make sure that the robot achieves that, right? And we are naturally switching to input output thinking then. So let's write this. So in this case, our input is the torque at the joint, tau, and our output is the angle of that link, or angle as measured at the joint, which is relative and absolute are the same. Okay, so to analyze this, we apply a Laplace transform of both sides, and then the form that we get, we put it in a certain ratio that is called transfer function. Okay, now there's a lot of things going on there, right? So first, what is Laplace transform? Laplace transform is nothing but a mathematical tool of representing that function in a different form, right? So there is a mathematical formula to it. So script L is representing Laplace transform of a function f, which is a function that is changing with time. So f of t, imagine, is like q of t or tau of t, which is some variable that is changing with time. And when you take Laplace transform of that, you go through some kind of integral equation. It's not important to remember this equation now. It's just to know that Laplace transform looks like some integral of this. But what you get out of this, you would notice there is s and t, but when you're integrating with dt with specific limits, you don't have any t left in your integral. What you end up with is a new function, which is only a function of this new variable s, and this s is called Laplace variable. Okay. As I said, it always looks confusing at first, but really what is it? This is nothing but a translation of this function from one representation to another representation. Right? So here it's a function of time t. Once you take the Laplace transform, you get a new function, which is a function of s, which is still representative of that same variable, just represented in a different manner. Right? So this, I tell people, people get lost in the math, but I tell people it's like just translating. Right? You take a story, you can write it in English, or you can translate it and write it in Hindi. That's all this is. It's like T is English, S is Hindi. So you're just translating, representing that function first in time, then in another variable. Now, why do we do that? And we'll see at least a little bit of that in a second. It has certain advantages once you translate it. It's the same function, nothing has changed. You've just written it mathematically in a different form. Right? There are certain advantages. So this is a bad example, but let me use a bad example. So let's say, the same story, you wanted to communicate with, somebody in Europe. Right? Then maybe the best way is to send the story to them in English. Of course, you don't know German or French, so you cannot translate it. So you send it in English. So in that particular scenario, it's convenient to keep the story in English. But supposing your focus was only correct pronunciation, then English is a very bad language to practice not practice, but to have correct pronunciation, because the same word can be pronounced many different ways, and if you send it to somebody else, they will pronounce it differently. So in that case, Hindi may be useful, because Hindi you cannot go wrong with pronunciation. So you can see when you have your objectives very different, it's not the same objective. In one case, you're only focused on pronunciation. In the other case, you're focused on, you send it to an unknown person. With that person, what is the chance that that person will understand? So both have their advantages, right? Of course, there are, this is, as I said, bad example, but you got the idea, right? The translation between different representations. In each situation, you could have different advantages. So when you represent a variable in terms of time, it's very easy to see how that variable will change over time. So you want to find out, what the angle will be 1 minute later, 2 minutes later, 10 minutes later, 20 minutes later, then it's most convenient to keep it as a function of time, keep it in this representation. You can draw graphs, you can record data, all of that, right? But if you wanted to analyze how this variable will behave under many different scenarios, then representing in terms of time is not very convenient, because if you wanted to see how this variable behaves over a 1 hour time window, and you wanted to see how it will behave in 1,000 different scenarios, then you really have to wait for 1,000 hours to find out how that variable will change over a 1 hour window in 1,000 different scenarios, right? So it's not very convenient, not very compact. A Laplace domain representation helps you with that. It's a very compact representation of how this variable behaves with different, in very simple terms, you can think of this as at different frequencies. High frequency, how it looks like; low frequency, how it looks like, and so on and so forth. So, by the way, this is not very far from your Fourier transform. This is closely related concept. You remember, you take a time domain signal and you want to find out the frequency content of it, you do a Fourier transform. So this is somewhat similar. Okay, long story short, all you need to remember from here is you can take the Laplace transform of any signal that changes with time, and you get the representation of that in terms of a different variable s, which captures more of the frequencies in the signal. Loosely speaking, that's all you need to know at the moment. Okay, now how does this help us here, and how does that lead to a transfer function? Okay, so then what we do is, let's call this equation 1, and we take Laplace transform of equation 1, and when we say on equation 1, we mean on both sides. And to keep it consistent, usually we write in the time domain small alphabet, but when we are transforming it, the convention is to write it as a capital alphabet. As I said, it's the same thing but different representation. So, okay, we do this. I, B, M, G, L are all constants. So they are not affected by the integral or the Laplace transform. They all come out of. So really, we are only taking Laplace transform of these variables. Right? And then there is another very useful property of Laplace transform that helps us over here, which is Laplace transform, or let me write it over here, because this is a reference we can use here. Laplace transform of the derivative of that same function is equal to, is a very convenient property, is equal to the Laplace transform of the original function. So original function Laplace transform of f of s multiplied by the variable s. But this is only true under this assumption. If the initial conditions are not 0, you do get another term. But as I said, we don't need to worry about it because we have already made this assumption. Okay, so let me erase this better. So s f of s. Then if we take the Laplace transform of f double dot, essentially you will just get s squared. So every time there's a derivative of a function involved, then you are in the Laplace transformed domain, you are just multiplying it by s. Okay. Don't worry about the meaning of all of this. As I said, it's a little mysterious, but just think about how to use it, and it's relatively straightforward, right? So we take Laplace transform on both sides. As I said, I, B, M, G, L comes out of the integral because Laplace is really some kind of integral. And then Laplace of Q double dot using this property will be S squared multiplied by Laplace of Q, right? So I get I times S squared times Laplace of Q, and I did say the convention is once you take Laplace, you use a capital letter. So Q of S. I hope you got that. I comes out of Laplace, then Laplace of Q double dot is S squared times Laplace of Q, and Laplace of Q of T is just capital Q of S. Different representation of that same variable. Right, so likewise B times one derivative, so S times Q of S plus MGL. Here it's just Q of S, the whole thing is equal to Laplace transform of tau of T, which again I'm writing it as a capital letter. Okay. Now for just keeping things clean, let me erase this. As I said, you can forget about it. All you needed to know was this property, and that this was a different representation of it. Now what this helps you do is, here to find Q, you really needed to solve a differential equation. And if you remember from your first year, second year math, solving a differential equation, can be a complicated affair. In this case, it's simple, but in most cases, it can be a complicated affair. But here, you can just take everything, rather, you can take Q of S outside as a common factor, everything else becomes one term, and then it's very simple. Then you can write this as IS squared plus BS plus MGL times Q of S is equal to tau of S. And if I move things around, I get Q of S divided by tau of S is equal to 1 over IS squared plus BS plus MGF. This ratio of Laplace transform of the output variable divided by Laplace transform of the input variable, this is really called transfer function. Now that you have this robot represented in transfer function form, which is the Laplace transform of the output variable divided by Laplace transform of the input variable, this can be used, it's useful, I would say, at least in 4 different ways. Okay. Before we go there, just again a simple observation, transfer function is typically some ratio of polynomials in S. So it has a very standard representation that facilitates all kinds of analysis. We don't need to understand how to analyze it now. Here the whole idea is understanding what is transfer function. And so far, just to recap, it is nothing but representing the relationship between the input and output variables. In our case, a robot, but you can do this for any other physical system also. But representing that in terms of the Laplace variables, and that gives you a compact form, and it gives you at least 4 advantages. Or we can use this in 4 different ways, or rather, they are widely used in 4 different ways. Okay, what are those? 1, it's, as I said, very useful form or very convenient form to analyze how the output would behave for different kinds of input torques. And when I say different kinds, the most common way to think about it is different frequencies and magnitudes. Large torque, small torque, and high frequency torque, low frequency torque. And any general signal, you can always think of it as a combination of different frequencies. So it's actually a very convenient form to analyze. Electrical guys will understand. For mechanical guys, it's a little bit unusual concept, but that's so first one is analyze how the output behaves under many different conditions in a relatively compact manner. Right? There are many analysis tools for that. We will not get into that. Right? It's just convenient to analyze. Here, as I said, you have to do many simulations, many solutions to figure out how it behaves under different conditions. The second way in which this is used is there are a whole bunch of tools that helps you figure out how to pick your input torque for you to get some kind of desired behavior of your. And again, we will not get into that, but that you can think of as control design. How are you going to design a controller that is picking the right torque to achieve some kind of behavior, desired behavior of the joint angle in this case, and in general it can be any output. The third way in which this is used a lot is this is also an analysis tool really, but to understand stability. Stability is a concept that is used widely in controls. We will not get to it in this lecture or even in this course, but just something for you to keep in mind that no matter how you design your controller, you want the system to behave in a stable manner, and there's a rigorous definition for it. We don't have to worry about it now, but transfer function form is a very convenient form to analyze that. And then the fourth one, which is a very powerful utility of transfer function, is that it's very convenient in transfer function form to combine multiple subsystems. It's very convenient. So what I mean by that is, supposing here you say, oh, the torque is again produced by motor. Motor has its own inertia, it has its own back EMF, it has its own dynamics. Then you write another differential equation representing how the motor torque changes as the motor voltage changes. Right, motor voltage or motor current. Again, there are, you can write down the differential equation representing that. Now, that differential equation and this differential equation, if you wanted to combine, you want to find out the combined effect of, if I apply voltage to the motor, how does it affect the torque, and consequently, how does it affect the joint angle? If you wanted one compact representation of that, you wanted to combine both those differential equations. Then combining differential equations is a complicated affair because you have to do convolutions. But in transfer function form, it's very convenient because you can simply multiply them together. So combining multiple systems or subsystems is very convenient in transfer function. So these are four major reasons why transfer function form is very convenient and widely used in controls. If you want to get into all of these are all again things you can read about. You don't need them right now, but at this moment what is important is understand what is transfer function, and then in the context of our robotics, the relationship between torque and the joint angle but represented in the Laplace domain. And this only works under these assumptions, and it is extremely useful to do these four.